Okay, I'd like to go through a second example of where we draw, with one-dimensional motion, we draw an example of position versus time, velocity versus time, acceleration versus time, and understand the relationship between those three graphs as functions of time. And I want to give you an example that is not constant acceleration. The previous example was constant acceleration. The car speeds up under constant acceleration, then coasts under zero constant acceleration, and then slows down under constant negative acceleration. I want to sort of get away from constant acceleration and give you a very rich and important example of non-constant acceleration. So that's the example of simple harmonic motion. So simple harmonic motion, for example, is a harmonic oscillator, mass on a spring. So we've got a spring, we've got a mass stuck on it, and that mass is oscillating back and forth with sinusoidal motion, a simple harmonic oscillator or simple harmonic motion. This is, hands down, the single most important system that as a physicist you need to understand. I mean, not only is it important for things like in physics 122 when you start talking about waves and so on, but it goes throughout all of your physics education up to like quantum field theory. We mentioned at the beginning, quantum field theory is a unification of special relativity and quantum mechanics. You get fields, and these fields are quantized. And it turns out that mathematically, quantum field theory is largely just harmonic oscillators. One harmonic oscillator located at every single point in space, all oscillating, independently in like a wave-like motion and so on. And then those oscillators are quantized, and the energy levels of a harmonic oscillator, the quantum energy levels of a harmonic oscillator are quantized. They occur at certain discrete points, this energy, this energy, this energy. And then it turns out that, roughly speaking, when you jump from one energy level of a quantum oscillator to the next, that corresponds to adding a particle, like a photon, to the field. So a photon is an excitation of the field. You've excited the field, added another photon. You've taken the harmonic oscillator from one energy level up to the next. So the point is just that harmonic oscillator, simple harmonic motion, is extremely important to understand as a physicist. You need to understand it left, right, inside out. Okay, so this is a great example also to illustrate, as I said, position versus time, velocity versus time, acceleration versus time, where the acceleration is not simply a constant. Okay, so it's a great example that I really encourage you to think about deeply. Okay, so harmonic oscillator. So the idea is we've got a wall here, and we've got a spring, and that spring has some spring constant K, and attached to the end of the spring is an object with an inertial mass m, a little block, and that block can slide back and forth on a horizontal frictionless surface. Okay, and so along the x-axis, and we will suppose that at x equals 0, this is called the equilibrium position. When the mass is over x equals 0, it means the spring is neither compressed nor stretched. So there is no force acting on the mass as it slides through the equilibrium position. Okay, and we will suppose that we've pulled the mass back, released it. So now the mass is the spring is compressed, and the spring is stretched. And the spring is pulling this way, and it accelerates the mass, and the mass oscillates back and forth like this. You just pull the mass out here, let go, and it oscillates back and forth between, say, x equals plus a, amplitude a, and x equals minus a. So it oscillates symmetrically back and forth through the equilibrium position between maximum and minimum positions plus a and minus a along the x-axis. Okay, and say at this instant of time, for instance, suppose we've released the mass, it's flying this way, it comes to rest, and then it flies this way. At this point in time, its velocity at that instant of time is, say, positive, to the right, but it's also slowing down. As the stretched spring is exerting a force that way, the mass is accelerating that way, its velocity is getting smaller, it's slowing down, momentarily comes to rest at x equals plus a, and then starts its cycle again. So at this instant of time, the acceleration is in the direction of the force that the spring is exerting on the mass, and the acceleration at that instant of time is, say, negative. Okay, so that's the kind of picture. And we say that we can describe the force that the that the spring exerts on the mass. So the force, the x component of the force, okay, is a function of time, okay, and it depends just upon where the mass is along the x-axis. So you can think of it as force as a function of time or force as a function of position. So that force is, of course, given by Hooke's law. It's proportional to negative x. It's negative kx, where k is the spring constant. Okay, so when k is larger, it's a stiffer spring. When k is smaller, it's a more slack, relaxed spring. Okay, larger k means larger forces for given displacements. Okay, so it's like that. And the most important thing about this system, one of the most important things, is what is the period of the oscillation? So the period is the time it takes the oscillator to get from, suppose you pull it back like this and release. It's the time it takes the mass to go, the oscillator to go through one full cycle. So the mass to go from x equals plus a through x equals 0 to x equals minus a, and then back to x equals 0 and back to x equals plus a. One full oscillation of the system. That's the period t. And I can just tell you what the answer is for the period t, but I wanted to use dimensional analysis, show you how awesome dimensional analysis is. So the period t, well, what could it depend upon? Well, there are only two parameters here. There's the spring constant k, stiffer or more relaxed spring, and the mass, the inertial mass, how sluggish it is, how much force you have to apply to get a given acceleration. So the period t must depend upon just k and the mass, spring constant and the inertial mass of the object on the end of the spring. And so what we want to do is we want to figure out, well, how exactly does the period t of this oscillation depend upon the spring constant and the mass? Well, we can just use dimensional analysis. So we say the period t, okay, well, that has the dimensions of time. Okay, we're using the same letter, t, dimensions, as for the period t. So, you know, whatever, there's only so many letters in the alphabet. Okay, so the dimensions of the answer we want is a time. The dimensions of mass, okay, that's easy, that's just capital M. The dimensions of k, so the spring constant, dimensions of the spring constant, we put square brackets around our variable. What is that? Well, if you look at the formula, k is a force divided by a displacement. So it's the same dimensions as force divided by x. The dimensions of force are the same as the dimensions of mass times acceleration. So mass, acceleration is length over time squared. Divide by a length. Okay, so that cancels out. And so we have the dimensions of k are mass divided by time squared. Now the idea is we're trying to construct some algebraic expression involving k and m that will give something with the dimensions of t, or time. Okay, and so you look, well, there's a t in there, a t squared. We need to get rid of the m, but there's an m there. So you can clearly see that if you take m divided by k, let's do that. The dimensions of m divided by k, what's that? The dimensions of mass are m. Divide by the dimensions of k, mass over time squared. The masses cancel out. 1 over t squared in the denominator becomes t squared in the numerator. So this particular combination of these variables, k and m, namely m divided by k, has the dimensions of t squared. We want to construct something with the dimensions of t, or time, the period of the oscillation. And so we just take the square root of both sides. So the square root of k over m will have dimensions square root of this, or square root of this, or t, and we're done. Okay, and so we can guess that the period of this oscillator will be proportional to, remember that dimensional analysis only gives you an order of magnitude estimate up to a dimensionless numerical factor. So we say the period t must then be proportional to the square root of the mass divided by the spring constant. And then you think, well, that makes sense, because I know that for a given stiffness of spring, if I make the mass larger, then we'll have given forces, larger mass, everything is more sluggish, the accelerations are slower, it'll take longer to speed up, it'll take longer to slow down, it'll take longer to speed up again, it'll take longer to slow down. The period will be larger if you make the mass bigger. And in fact, you can see that if I make the mass 4 times as big for a given spring, the square root of 4 is 2, I will double the period. So given an oscillator, if I quadruple the mass, I will double the period, how long it takes to go there and back again. Or, similarly, k is in the denominator, because if you increase the spring constant, make the spring stiffer, that means the forces are larger, the accelerations are larger, it'll take less time for the mass to get from here all the way to there and back again under greater forces, greater accelerations. And so larger k in the denominator means smaller period. Again, if you quadruple k, put 4 springs in parallel, you will exactly 1/2 the period, right? Okay, and so this proportionality turns out to be a 2 pi. So if you actually work it out, you'll find that the period is actually 2 pi, a dimensionless number, times square root of m divided by k. And so that tells you that the frequency, okay, how many cycles per second, okay, you go 1 cycle per time t. So the frequency is 1 over the period. So 1 over the period will be 1 over 2 pi times the square root of inverting, square root of k over m. Square root of k divided by m. Okay, so larger spring constant, stiffer spring means higher frequency. Smaller mass means higher frequency. Smaller mass in the denominator. Okay, and then one other thing we need to know for notation is the angular frequency. Omega is 2 pi divided by the period. So if you've studied anything to do with harmonic motion, you'll know that you can represent harmonic motion as it's closely related to circular motion. And so associated with a cycles per second kind of frequency, there's an angular frequency. So it'll go through 2 pi radians, 1 full circle, 1 cycle back and forth in a time t. So omega is 2 pi divided by the period. So take 1 over the period multiplied by 2 pi, and you get that the angular frequency is the square root of k over m. So that's omega. So that's an important relationship. Okay, great. Now, what we want to do is we want to sketch. We're going to take the mass, move it to a displacement a away from the equilibrium position, and release. And we're going to sketch the position versus time, then the velocity versus time, and then the acceleration versus time. Okay, so great, let's do that. Let's do position versus time first. X as a function of time. Okay, and we'll be interested in t equals 0 is when we first release it. That's t equals 0. And then we're going to watch its motion, x as a function of time, for 1 full period. It goes from here, there, all the way back. So it ends up at time capital T. So at time 0, it is located at x equals plus a. So at time 0, it's located at x equals plus a. And then after 1 full period, it's located back again at x equals plus a. Okay? And then, so how do we reason about, filling in these 2 points, the graph between these 2 points? Well, it's obviously not just going to be a straight line. Okay, so there's going to be something. So let's think about this a little bit. So it takes a time capital T to go from here all the way to here and back again because of the symmetry of the problem. Remember, symmetry is a very important principle. When you can apply it, do so. Okay, so obviously, it's going to take, because of the symmetry, it's going to take exactly half of the full period to go from here to here. So exactly at the halfway point, t divided by 2, the mass is going to be located at x equals minus a. So that's down here, minus a. It's going to be located down here. Okay? And then you say, well, here, when you release it, it's speeding up. It reaches its maximum speed here, and then it's slowing down. Again, because of the symmetry, the time at which it's going to be passing through the equilibrium point the first time, this is half a period. Well, that's going to be a quarter of a period. So a quarter of a period is here, 3/4 is here. So at 1/4 period, the mass is passing through x equals 0. So at 1/4 period, it's passing through x equals 0. So that's another point on the graph. Okay, and then it comes back 1/4 of a period later, it's at x equals minus a. 1/4 of a period later, it's again passing through x equals 0 in the opposite direction now. So it's here, and then it ends up over there. And so now we have actually 1, 2, 3, 4, 5 points on its position versus time graph. And so now we just fill this in. Now we could fill this in with straight lines, but of course that answer won't be right. And so we know that this, we can just see from this motion, it's not constant velocity from here to here, and then constant velocity from here to here. It starts off with 0 velocity. So its initial slope is 0. And then that slope increases as it the velocity is negative, so it gets increasingly negative, so the slope goes down, and what you're going to fill in these dots with is a nice sinusoidal function. Okay, so actually a cosine function. So a cosine function looks like this. Okay, so there you go. So that is the position as a function of time, and you can see that, that at this point the slope is 0, the velocity is momentarily 0 when you release it. Okay, and then at this point, the velocity of the slope is 0. When it reaches x equals minus a, it slows down, comes momentarily to rest, 0 velocity, 0 slope, and then it increases positive velocity. Okay, slope increases until it has maximum velocity when it passes through the equilibrium point, and then that velocity, that slope decreases to 0 at this point. Slope 0 here, 0 here, 0 here. Okay, so things like that. I'm hoping that you'll be able to think about things like that. So points and slopes. Okay, and that allows you to construct the graphs. Okay, now the next thing we do is we construct the velocity as a function of time. So this is the x component of the velocity. When the mass is moving this way, it's positive. When the mass is moving this way, it's negative. So the x component of velocity will be some function of time that we're going to figure out. This is the initial time 0. This is time t over 2. This is a quarter. This is 3/4 of a period. This is 1 full period. Okay? So it's the same time, the corresponding times in both graphs. Okay? That's a nice way to draw the graphs so that you can sort of refer from one to the other very easily. So the velocity, the x component of the velocity, is the rate at which the x position is changing. So in terms of calculus, it's dx dt. It's the slope. It's the slope of the position versus time graph. So of x versus t. Okay? So we can figure this out. So let's see. So let's just do it sort of graphically first and then sort of interpret it in terms of the real world, the actual apparatus there. So we say slope, let's just follow our noses here. Well, at t equals 0, the slope of this graph is 0. Okay, and then at t equals 1/4 of the period, the slope is maximum and negative. Okay, so at this point it's maximum negative. So let's call that negative Vmax. Okay, and then at this point in time at t at 1/2 the period, the slope of the position versus time is 0. That means that the velocity must be 0. So we have this point, and this point. And then when we get to 3/4 of a period, you can see the slope started out 0 here, and then it increased, became maximum positive at time 3/4 of a period. So it's maximum positive, so that's positive Vmax. Vmax is the maximum speed. Negative Vmax this way, positive Vmax that way. Okay, and then finally, when we reach a full period, the oscillators come all the way back from its starting point, then the velocity, slope of the position versus time, is 0. Okay, so we have all these points, 1, 2, 3, 4, 5. Again, how do we connect the dots? Well, we're not going to do it with straight lines, okay, because these velocities are not, these accelerations are not constant. The accelerations are directly related to the force, and the force is not constant. The force is large here, it's 0 here, it's large in the opposite direction there. So the force and the acceleration are not constant, so the velocity versus time graphs will not be straight lines. And so it's basically the derivative of a cosine. This is a cosine function. The derivative of a cosine is a negative sign. And so you can just connect the dots with a negative sign. So it looks like that. Great. So that is your velocity versus time. And you can see that the velocity is equal to plus or minus Vmax, okay, plus Vmax or minus Vmax at this point in time and at this point in time. That's a quarter period and 3/4 period. Okay, so that's happening. This is a quarter period. You release, you let go, you wait for 1/4 of the period, and the mass is passing through the equilibrium position. This is half period, this is 3/4 period, so 1/4 and 3/4 correspond to the mass passing through x equal to 0, passing through the equilibrium position where the force is 0. And that's where the velocity is maximum. And you can see that because if you start here, the velocity is 0, you let go. the force, the spring is stretched. It is exerting a force this way. And so it's increasing the velocity in the negative direction, okay, until it passes through the origin, the equilibrium point. Then the spring starts to compress, exerts a force that way, reducing the velocity down to zero again. And so the maximum velocity happens when the mass is passing through the equilibrium position, here and here, or here negative Vmax, here positive Vmax. First negative Vmax, next positive Vmax. Okay, so that makes sense. So this is V is equal to plus minus Vmax at, when the mass passes through the equilibrium position, x equals 0. So that all makes sense. And then you can look at the acceleration versus time. Okay, so the same two instants of time, t equals 0 and t equals capital T. Here's the midway point, and here's the 1/4 and the 3/4 of a full period. Okay, so again, the acceleration is the rate at which the velocity is changing with time. That's the same thing as the instantaneous slope, the slope of a line tangential to that curve. So that's the slope of the velocity versus time graph. And so again, we'll just sort of follow our noses graphically, and then we'll interpret in terms of the apparatus, like what's really happening. Okay, so at this point, at t equals 0, the slope of this function is maximum negative. So it starts way down here. So this is negative a max. So at t equals 0, negative a max. And then the slope gets, it's always negative here, but it gets less and less negative until at 1/4 period, the slope of the tangent line is 0. Okay, and then the slope starts to increase, gets larger and larger positive until it's maximum positive at exactly 1/2 period. So 1/2 period is up here, and this is positive a max, where a max is a positive number. And then we come to 3/4 of the period, the slope is maximum positive, and then it decreases, and it becomes 0 at this point. So the slope is 0 at that point. And then the slope becomes negative, increasingly negative until it reaches negative maximum value at the full period. So that's down here. Okay, so again, we have points, 1, 2, 3, 4, 5. How do we connect them? Well, we connect them with a smooth sine or cosine kind of function. And so we start like this, and we go up. Let me move this a little bit over so it's a bit nicer. So it starts out with 0 slope, and then it goes up, maximum slope, and then 0 slope, and then maximum slope, and then 0 slope. Okay, and so the graph looks something like that. Okay, and so you can see, where is the acceleration maximum? Let's see if this makes any sense. We're always trying to think like physicists. We're always trying to connect our diagrams, our equations, whatever, our thinking with the real world to make sure we're always on track. Does this diagram make any sense? Well, let's see. What it says is that the acceleration in the x direction is maximum, so it's plus or minus a max. It's plus or minus a max when x is, it's plus a max when x is when time is half the period, or the initial or final time. How did I write that? When x is equal to minus plus a. I guess that's the easiest way to say it. So a is equal to plus or minus a max at x equals minus plus a. Okay, so when x is equal to, this is x as a function of time, when x is equal to plus a, that's either here or here, what's the acceleration? Well, the acceleration here and here is negative a max. When x is at negative, when the mass of x equals minus a, then sorry, let me say this the other way. When the acceleration is positive a max, that's at time t equal 2, we see that x is at minus a. And so how does that make sense? Well, if we look, when x is equal to, say, plus a at this point, the spring is maximally stretched. So the force that the spring exerts on the mass is maximum, and it's maximum negative. It's to the left. Okay, the force on the spring is to the left when you're at x equals plus a. So at this time and this time, the force is maximum negative, means the acceleration of the mass is maximum negative. So the mass momentarily comes to rest here, and then it turns around and starts going this way. The maximum acceleration happens here and here at x equals plus a and x equals minus a, where the acceleration is maximum negative and maximum positive when the spring is maximally compressed. Force is maximum, acceleration is maximum. Okay, so all of this, you need to compare these graphs to each other and to the real world and see that it all makes sense. Okay, physics is all about, does it make sense? Okay. Now I want you to observe something really cool. So you'll notice when you just compare this graph with this graph, you'll notice that this graph and this graph are identical, except they're of opposite sign. When this one is maximum negative, this one is maximum positive. When this one is maximum positive, this one is maximum negative. So this graph and this graph are identical, except they're just multiplied by a minus sign. Okay, and so you can observe just graphically that the acceleration at any instant of time is proportional to negative x at that time, with some positive proportionality constant. And then you think, well, the acceleration of that mass, well, that's just proportional to the force. So this is just saying that the force at any instant of time is proportional to negative the position at that instant of time. And of course, that's exactly true, because the force is minus kx. Okay, so force, that proportionality constant, is in fact just k, the spring constant. So you see Hooke's law in this graphical, in the relationship between these two graphs, position versus position and acceleration, or position and force. Force and acceleration are just directly proportional to each other. Okay, so that's an interesting thing to observe. So that's just Hooke's law. But now here's something also interesting. If we look at the maximum acceleration, okay, so when you solve physics problems, it's not about getting some answer. You know, oh yes, the distance the ball moved was 10 meters. You know, who cares? What you're interested in always, for all the physics problems you solve, is trying to understand everything you possibly can about the system. Just stare at it and think about it. So for instance, A max here. So A max, which we know happens at, the turning points, x equals plus a and x equals minus a, that maximum acceleration is going to be the maximum force divided by the mass. F equals ma. So the maximum acceleration is the maximum force divided by the mass. Okay, well, what is the maximum force? The magnitude of the maximum force, well, the force is minus kx. The magnitude of the maximum force will be k times x maximum. X maximum is here or here. Okay, and so F max is k times a. Okay, and then divide by m. So that's interesting because we know this ratio k over m is important. Okay, when we did this dimensional analysis, we figured out that the cycles per second is proportional to root k over m, or the angular velocity of this cyclical motion here is the square root of k over m. Omega is the square root of k over m. That's what characterizes the frequency is spring constant divided by mass square root. So here is spring constant divided by mass, not square root. So that means that k over m here is omega squared times a. So this is a really interesting relationship. So you see that the maximum acceleration of a harmonic oscillator going back and forth, it's accelerating maximum here in the negative direction, it's accelerating maximum here in the positive direction, and the magnitude of that maximum acceleration is proportional to or equal to omega squared times a. So keeping everything else the same, if you double the amplitude, if you pull this thing back twice as far and let go, then your maximum acceleration will double. Okay, but more interestingly, if it's oscillating back and forth at twice the angular velocity, then this is squared, and so it's 4 times. The accelerations involved are 4 times as large for twice the frequency of oscillation. So dimensional analysis and simple sketching of curves relating position, velocity, and acceleration versus time allows you to discover important basic things about and sort of get a deeper understanding of the physical systems that you're looking at. Okay, so the power of dimensional analysis, the power of sketching things, visualizing things in your head, understanding slopes, understanding all that kind of stuff. Super important stuff. This is a great example. It's probably the only example you'll see in Physics 121 of a non-constant acceleration case, which is the usual case in the real world. Constant acceleration is a very, very special and artificial case. Okay, so anyways, so here's a nice rich example illustrating drawing position, velocity, and acceleration versus time.